Hey there, everyone. I'm John O'Connor, and welcome to Code Your Face Off Live, a weekly radio show, or YouTube show, whatever the heck this is, where I go over topics in computer programming, variety of topics in computer programming. They're mostly things that have been distilled from mentoring sessions that I've figured out over the week that I've had to answer the same question multiple times. When multiple different students ask it, I figure why not just create a little show where we can kind of talk about this stuff. They're topics that come up all the time for beginning programmers, intermediate, advanced programmers, really all over the board. So this week, we're going to be talking about designing software. How do you design a computer program? How do you design something really, really, really big? A lot of my students will come through a program, they'll do a curriculum, and that curriculum kind of shows them, holds their hand throughout the process of creating something, like an RSS reader or something, video game. And then when they actually go to do it themselves, they're kind of stuck thinking, well, what do I do now? How do I build my own now that I've built somebody else's? How do I really design my own software? So today's sessions, we're going to talk about that. We're going to cover how do you design software kind of from a high level. We're going to mix a little bit of JavaScript, a little bit of Java, but this material really could apply to just about any programming language. And it's kind of a good skill to have anyway. So that's what we're going to talk about today. Let me get you guys started. So the two pieces we're going to talk about, one of them is thinking in an object-oriented way. You'll hear the term object-oriented a lot. I'm going to explain kind of what that is, what the concept is of it. We're going to go through a few details about how certain pieces of object-oriented programming work. And then we're going to talk about something called design patterns. They're a very fundamental piece of software engineering, and it's something that's not often covered, at least not in any kind of depth. So today I'm going to give you a primer into design patterns. I'm going to talk about some common ones, and we'll cover a few of those pieces. So that's going to be the plan for today. If you're joining me live, I have opened up on the Code Your Face Off lesson. If you go to cyfo.usefedora.com, if you have signed up, which you're probably watching this, you have already. If you go to the lesson, you're going to see that there's actually a little form. It's a Google form, and that form you can use to submit questions to me throughout the show. So if you want to head on over to that lesson page, you're going to see a little Google form on the bottom right, and that's going to allow you to ask me questions live in the show as we're going. So feel free to submit questions to there. I'm going to check it periodically. I'm actually going to pull it up right now just so I have it there, and try to answer your questions as we go throughout this show. So that's the introduction to it. And I'm going to go ahead and just kind of jump right in here. So the first thing I want to talk about is the concept of object-oriented programming. You've kind of heard of this before, probably if you're working in, especially Android. You've heard of object-oriented programming, but do you really know what it is, or does it make sense to you anyway? So I'm going to go over that a little bit right now. So whenever you're designing an application, whenever you're designing software, and actually I should back up a little bit. The idea of object-oriented programming actually comes from an engineering crisis that happened in the 1970s. It was a software engineering crisis. And in the 70s, around that time frame, software was beginning to get really complicated. And software engineers didn't have the tools to actually build good, complicated software. So we had software that was coming out that was not working very well. We had software on the stock market that was crashing constantly. Just to name one example. So really something needed to be done. And what they did, software engineers, researchers, they looked to the hardware engineering field, to the systems engineering field, and they said, well, how do you build a large building? How do you build a bridge that lasts and that's usable? And they took a lot of those concepts and they sort of turned it into an idea in code where they said, what if we thought about our code as in concrete terms, in terms of objects around us interacting with different things. And we created just a simulation. So our software, all it is a simulation of some real world interaction. And that would allow us to build larger complex software while still keeping it, in the realm of conceptualizing for a person, right? So made it possible for them to actually be able to conceptualize it. So that's what object-oriented programming, that's where it came out of. And when you're starting to think about object-oriented programming, what you really want to do is find a way to decompose your problem into a set of concrete objects that you can think about real objects, real interactions between objects. And that's how you design object-oriented software. So I'll use a quick example, and what I'll do is I'll share my screen, and I'm just going to walk through a very quick example in Java of how to do some object-oriented programming. And Java is a language that is, in its nature, object-oriented. Everything in Java, with very few exceptions, is actually an object. So I'm going to go ahead and pop on over to the screen share. I'm going to share this IDE1 site with you guys. Let's do this. So I use IDE1 every once in a while. I was going to use Android Studio, but it actually crashed on me. Go figure. So let me go ahead and make this a little bigger. And there we go. Cool. So we're going to start out with a pretty simple example. The concept would be that of a dog, right? And in this, this is an example that's used often in programming. They'll use animal, dog, those kinds of things, because they're easy to think about. Maybe what you can do if you want to make it more lively is imagine this as a dog in a game. So you're in a video game, and this class right here is going to be an implementation of a dog. So this class represents dog inside of your application, inside of your game. Let me get rid of that. And let's get rid of that. So now we just have class dog, right? So when we think about this dog, we have to think about what are the different parts of a dog, a physical, concrete dog. And what are the parts that our application, that our game wants to interact with? So let's say that we want to, create pieces of this dog so that we can move them around. So let's add some legs to this dog. Let's say we'll create an array list of legs, and this array list is just an array. Legs equals new array list, and we'll give it a size of 4, right? So this dog has 4 legs, and we'll say that this dog has. Well, that's a good start for now, right? We're just talking about the idea of breaking something apart. So now we have this new leg class here that we've created. And we can create this leg class down here. Now, you're allowed to do this in Java. In fact, any object-oriented language, you're allowed to decompose your object, and you're creating new objects as you're decomposing it. So what I did was I said I wanted to have these legs in here, so I created a new class. I just made it up called leg. And then I have to go in later and implement that leg class. So my class leg, I'm just going to leave it alone right now. It's not going to really do anything yet. And it doesn't need to do anything for this example because I'm just using it to show how you decompose a project, how you decompose something. So this dog, right, it could have a, let's see, what other things? We could give it maybe a snout, right? And we'll give it a tail. And that's all I'm doing here is just decomposing this dog into separate pieces, into separate objects. This concept of composition is extremely important in software engineering. In fact, pretty much everything that you see related to software engineering, things like design patterns, which we'll go over a little bit today, language constructs, all of these things are based on the idea of composition. Because composition, how you put, being able to put a piece together or 2 pieces together to make one whole, that concept is very powerful in software engineering. It's pretty much the most important concept that we have. That's how you build large things, is you compose it of smaller things. So we have a class leg. I'm going to create a class snout down here. And I'm going to create a tail T, or class tail, my mistake. There we go. And that's really all we do when we start out a project. We start with the main thing that we're thinking of. In concrete terms, in real world terms, what am I thinking of? I'm thinking of a dog. So I write down class dog. And you'll see some people, you'll see, sometimes as you're working through your code and you're thinking about these concrete things, you realize that you have a class dog in your game. And let's say it's something like, Sims, you need a class cat, and you need a class bird, and you need these other classes. And you start to recognize that this class cat and this class dog, they share a lot of things in common. You have another array list of legs. It's the same basic thing. You have another snout, and you have another tail, right? So this class cat and class dog, they share a lot of things in common. In fact, it might be kind of nice to say, why don't we take these pieces that are, common to all these animals, these 4-legged creatures, and let's create a class that represents 4-legged creatures, right? going to create a four-legged creature class. And rather than including all of this information in cat and dog separately, why don't we just put them inside a four-legged creature? And why don't we say that cat and dog are now a special type of four-legged creature? And that's what we're going to do here. We're going to say this class cat is now a special type of four-legged creature. It has all the features of four-legged creature, but it's also got this extra stuff in it as well. And it doesn't matter what exactly the extra stuff is. The idea here is just that, you know, when you have this functionality that's shared across multiple pieces in your application, and you notice that they're all kind of the same, you can extract that into what's called a base class. And here, this four-legged creature, you know, this is kind of in itself an object, but it's not something that we would create. You know, there's no such thing as just a four-legged creature in and of itself. Every animal is a four-legged creature, but you couldn't create a four-legged creature out of thin air. There's no real implementation, as we would say, of this four-legged creature. So in programming terms, this idea of having this common set of features, but not necessarily being able to create one of its own. In this case, a four-legged creature, it shares a lot of properties with other stuff, but it's not really its own animal. This is what we call an abstract class. So an abstract class is a class that can't be created by itself. It needs to have some kind of specialization. Other things can derive from it. You can have a specialization of this four-legged creature and call it a cat, and then you can create a cat. But you can't really create just a four-legged creature. And that's the idea of abstract classes. And this is an important idea in object-oriented programming as well, because now you have a class that covers a certain functionality level, but it doesn't actually exist by itself. In Java, you'll see a lot of these abstract classes, and Java is a language that's very heavy on design patterns. So you'll see a lot of these design patterns, a lot of these concepts in Java, because it's a very heavily object-oriented language. If you've been doing the Android curriculum for any of these online boot camps, for Block in particular, I know, they talk about abstract classes. And one of the common questions that I get is, what is the difference between an abstract class and an interface? That's a question I'm going to answer in just a moment, because some of you out there, this might be a little bit over your head still. I'm going to go ahead and break it down and talk about interfaces, and then I'll circle back and we'll talk about the difference between an abstract class and interface. And actually, I can talk about it a little bit now, but the idea here is that we'll talk about it right now. So you have this abstract class four-legged creature. It contains a lot of the features of a cat or a dog, but it can't be created by itself. That kind of stuff goes really well in a base class, in an abstract class. And we have here dog. We're going to extend four-legged creature as well. And that's one way to decompose an item, an object, right? We decompose the dog by thinking about, what is this dog? It's a four-legged creature. It has, legs. It has a snout. It has a tail. That kind of stuff. That's one way to decompose it. Another way to decompose it is to think about, what are the behaviors of this dog, right? What are the behaviors of this thing? And whenever you're thinking about behaviors, you'll think about maybe the dog can talk, right? Or we'll say maybe bark, right? So we'll create a method here. This is going to be a public method we'll call bark. And inside of here, we can, this is just a printing out to a console. It says ruff ruff, right? Now this dog is barking at us, right? And we have this method inside of a dog called bark. We can also have a method called walk. And, if this were a video game, this could be, start the walk cycle, for dog, whatever. Something like that, right? Start walk cycle would be a good one here. There's no real, this is just an implementation of it. And you'll notice this behavior idea with this dog, these are things that might exist in other creatures as well. Let's say we have a public void meow for a cat. But then we're also going to have a walk method for this cat as well. And the cat is probably going to walk a little differently than the dog, perhaps. The cat, instead of walking on the ground, it might jump up and walk on a fence I don't know, that's a poor example, but you get the idea. These constitute behaviors. So what we saw in here, these right here, these are properties of this four-legged creature, of this dog and this cat. And these properties take the form of variables. So we have a new array list of legs, we have a snout, we have a tail. These are properties of the dog. These methods here, well, these are behaviors of the animal, right? This behavior, meowing is a behavior, walking is a behavior. When you're talking about behaviors, that's when an interface becomes handy. We can create an interface, you know, let's say this public void meow, right? Let's say we want to make that more generic. We would like to maybe say, rather than meowing, we could just say talk, right? Or make noise, right? Vocalize somehow. That's kind of a generic behavior that covers meowing and barking. So we can create an interface. Let's see. Interface, what do they call it? Vocalize. And we're going to say that this public interface vocalize has a method called talk, right? So now you can call the talk method inside of this cat if it implements this behavior. So an interface is all about behavior. And when you're talking about interfaces inside of Java, you use the implements keyword here, vocalize. Now what will happen in a lot of your editors is they're going to say automatically, hey, if you implement vocalize, you have to create an implementation for it. You'll notice that this vocalize, this talk method, doesn't actually do anything. And in Java, this has to do something. When you implement vocalize, it means that you want it to do something. It has to do something in here. So we're going to have to create an implementation for it. And this will be automatically generated in a lot of your languages by your IDE, whatever IDE you're using. I'm going to just add it here myself. Void talk. And we're going to say, right? So the idea here, the difference between an abstract class and an interface is that an interface is used to describe behaviors, whereas an abstract class is used to abstract out or take out certain common functionality that multiple different classes might like to share. One thing that gets people confused now is that you can add behaviors to this abstract class as well. You can add the behavior of talk to your abstract class. And if you make it abstract, it'll actually even require all of these implementing classes, these child classes, it'll require them to create their own version of talk. So if you leave this as abstract up here, we can get rid of the implements vocalize. And now this is still going to require me to implement this method of talk because I told it in the base class here in this four-legged creature that, hey, this four-legged creature is going to be able to talk. I don't know exactly how it's going to talk yet, but it has to be able to talk. This is a behavior that is inherent in the four-legged creature. So two different ways to kind of get the same functionality here. And a lot of developers that I work with get confused between an abstract class and an interface. And the idea here is that it's a different way of decomposing a concrete idea. Yeah, a dog is where we started this whole thing, right? So it's a different way of decomposing a dog. The first way that we were talking about was to extract out features of the dog and behaviors of the dog and stick them in a base class that a bunch of other animals, four-legged creatures, can now use. The other way is to take some of these behaviors and turn them into an interface. So now the behavior is what we're actually decomposing. And it really just depends on your use case as to which one you want to use. There's no real wrong answer here. If I wanted to do talk as an interface, that's fine. If I wanted to put it in the abstract class, that's also fine. The reason that I chose to use this vocalize interface is I want to be able to use vocalize across other animals as well. Let's say I have another abstract class for bird-like creatures. So we'll say winged creatures. Right? I still want to be able to do a talk method in here. And so you can see now I've done this twice. I've got this extra method in here that I've allowed to exist, and I've had to copy and paste it. Anytime you copy and paste in code, you really want to think about it. If you have to do it more than twice, if you get to your third copy and paste, it means you probably should rethink your design. Maybe you should break those out into an abstract class. That's kind of a good guideline too, because whenever you copy and paste, you run the risk of, one, copying and pasting wrong and basically getting your code wrong. So now you have code that works in one class, doesn't work in another class, and it's the same code. That can be really confusing. The other thing that you'll notice too is that when you're going to debug code, it's kind of nice to have one place that you know this code exists. So if you see an error that you know comes from a certain chunk of code, you now only have one place to look. So it saves you a lot of effort when you're going back to debug. And when you're programming, you spend 90% of your time debugging. So that's kind of a useful thing to have there. So that's the idea behind classes, abstract classes versus interfaces. This all comes from, again, this idea of thinking in an object-oriented way, thinking about an object when you design your software. So you're not really thinking about software, you're not thinking in code. What you do first is you think about the high-level objects. What is my system, and how does it decompose, right? And a lot of times when I'm designing software, I'm actually going to be not even in a coding tool. Very often, I'm actually going to be inside of a drawing tool. Let me see if I can get this to pull up here. We're going to pull up Google Draw. I don't know why it's being silly about this today, but the idea here, I'll find it in a second here. So most of the time, I'll actually spend my time in a drawing tool where I'm sketching out different ideas rather than writing code about different ideas. You know what I'll do is I'm going to pull up OmniGraffle for you guys so you can see it. I'm going to give you just a little quick. I'm going to show you just a real quick tool. This is a Mac-only tool. There are plenty of other tools out there also that you can use to design software. I'm just going to use one that I've used before called OmniGraffle, which lets me kind of model these different pieces of software. Let me share that with you too right now. I'll go ahead and share the screen here. So you can see OmniGraffle pops up and it lets me choose a software design, which is what I'm going to do here. I want to do entity. Let's go ahead and do UML. Now you don't have to know this stuff. You don't even have to use UML. You can just use boxes. You could actually even go a step further and just use paper and draw sketches, right? I do that all the time as well. UML is a design language that allows you to communicate software design in sort of a more defined way. A lot of computer programming and computer science programs will teach you how to use UML. I don't tend to use it very often myself, but occasionally it comes in handy. So what I'm going to do is I'm just going to get rid of that, because all I really want is just to start drawing some stuff. Whenever I think of software, I think of, what do I have? I have a dog, right? And this is my game. I have a dog. And this dog needs to be able to do stuff. Let me go ahead and stop this and reshare a better one. There we go. Yeah, so you can see I just start with a dog, and I'll start with the behavior of a dog. Let's say a behavior would be, talking. This is a behavior I'm going to have in my system. I'll give it some kind of a differentiation. I'll say, I'll do a dotted line rather than a block line, just so I can tell, this is an interface, this is a behavior I want to implement, this is an actual object, a concrete idea, thing I want to implement. So I'm going to say that this dog, inside of it's going to have this talk functionality, right? And feel free to draw them however you conceptualize. I'm going to have it talk. I'm going to have it walk. I like that. Now this works for me. I like this. So this is what I'm going to do here. And I also have a cat here that's going to walk and talk. And both of these guys are going to get, they're both going to get the same treatment as a four-legged creature. You're going to have properties from this four-legged creature. And in UML, there are a couple of different, the arrows that you use, those have kind of a special meaning. I'm not going to do that right now, so I'm just going to draw out a couple of little, nothing crazy. I'm not going to go and do this. I just want to show you some of the arrowheads that we can use. That's the wrong side. Just to represent our idea, our system, right? That's all we're doing, is we're just designing this software right now. You'll notice that I'm not, this entire thing can be designed in code or in, visually. A lot of times I won't actually write a line of code until my software is completely designed. And that's very common in the industry, is to write your software in terms of the design first, and then go back and code it all up later. And that's a good way of making sure that your system works the way you want it to before you actually do any of the real work. This is one of the concepts that they got from engineering in general. Used hardware engineering, aerospace engineering, all these different engineering disciplines. They'll spend a lot of time planning out how pieces connect together, how components of your application work together. And then once you've got that, then you start to actually build component 1, component 2, component 3. And as long as the communication layer between them, as long as the agreements that they make hold, then your application will go together just fine. I'm going to show you a quick example of that. We're going to use a more complicated example. This is going to be a airplane, right? This is a jet plane. This is actually a real example from the aerospace industry. Let's talk, this is like the F-35, right? So I'm going to start with this idea of an airplane, right? This is going to be my entire airplane. This whole huge box is going to be my airplane. And let me give us some size here, because you guys can actually get to see more of this. This whole thing in here is my airplane. I shouldn't even call it airplane. This is an awesome jet, right? That's what this thing is. It's an awesome jet. And this entire jet is composed of a lot of different pieces. So what I'm going to do when I design this awesome jet is I'm just going to start with the highest level pieces. I have the flight controls. I have the cockpit. I have fuselage, which is the entire body of the plane. I always spelled this wrong. I'll go with that. Spelled it wrong, my apologies. We're going to go with the wings. We're going to have all these pieces to this plane, right? This is the tail. And that's what we're doing when we start out. We start out with the simplest possible concept, the highest level concept. I have this awesome jet. What do I do now? Well, let me find out what pieces go into this jet, right? Let's say this is our starting point here. We have all of these pieces together, and that makes sense. This is our entire application. This is our entire jet airplane for now. There are probably more pieces I'm missing, but you get the idea. And now I design, how do these pieces work together? Well, let's say the flight controls, they have to be able to tell the tail, right? There's flaps on the tail, so we're going to say that this one should be able to move the flaps on the tail. Let me just give this some kind of behavior here. Should be able to, oops. Sometimes it's a little hard to get the text right where you want it. I'm just going to put it up here. Move tail flaps, right? The flight controls are going to be able to move the tail flaps. Flight controls are also going to be able to move the wings. I'm going to create a little guy here. Another one right there. There we go. Same idea. We're going to be able to move the wings here. Right? So now we're talking about features of the flight controls. These are the things the flight controls can do. The cockpit contains the flight controls, right? This is where the flight controls are. This is where the pilot can get them, or can actually control the plane. So we'll call it a contains relationship for now. Eventually, I'm actually just going to stick this inside of this cockpit. But for now, we'll say it contains the cockpit contains the flight controls. And then the fuselage contains the cockpit. So you can see how we're modeling the relationships between these pieces. We say we know it has these pieces. Now I can see that there are relationships between these. So that's how we do this software development. And now all we do is drop down into each one of these pieces, and we create a brand new document here. Oops, let me see. Let's create a new canvas, and we're going to take the flight controls, and now we're going to break out the flight controls into their own giant piece. And I'm not going to go through the entire thing here, but you get the idea. Awesome ass jet, flight controls. So we take each one of these pieces that we created and we decompose it into more pieces down here. Decompose it into there, into there, into there. And we can take this further and further and further down until you have something that's intricately complex. And all it is composed of these systems of systems. We call it systems of systems engineering. And that's exactly the concept that we're using here. So that is, in a nutshell, how you design a large application, right? That's how you design a big app. You think about what the high-level system does, and you compose it of smaller systems. And this idea here of taking our big black box, and our, sorry, I lost my OmniGraffle screen here. Yeah, the idea here of taking this big jet and creating these black boxes in here. This flight controls box is just a black box. There's nothing in it yet. I'm just saying I know it has to be able to do these things. I know it has this in it. But I don't have any implementation yet. That's okay. That's black box engineering. It's totally fine. That's actually how we design very large systems, is you say, okay, I just know that it's going to do these things. I don't care how. And that idea is actually one of the fundamental pieces of composition of designing software. And black box engineering is the term that you'll hear bandied about there occasionally. Right. So when you're thinking about creating behaviors in something, that black boxing, that's called coding to an interface. So you'll hear terms like tight coupling versus loose coupling. I had a good question earlier this week. What is tight coupling? What is loose coupling? Tight coupling is when you say, I need to know that this flight control, what this black box flight control, I need to know what's inside of it. And I need to know what's inside of that thing and inside of that thing in order for my fuselage to work. And when you tightly couple this flight control, the details of this flight control with this fuselage class, that means that if you make a change here in the flight control, somewhere deep down, way inside the depths here, you're going to cause the entire app to break. Your fuselage is going to break because something deep down in the flight controls changed. If you instead think, oh, I don't care what the flight control is doing, all I know is that it needs to have this behavior. It needs to be able to move the tail flaps and move the wings. If it can do that, I don't care how it does it. Now your fuselage can contain this flight control and nothing's going to break. If you change your flight controls, you can change it all day long. Your fuselage is going to stay exactly the same. It doesn't care how the flight controls work as long as it does what it says it's going to do. I like to call that a contract, right? So if you're writing a code with multiple developers and you have one person in charge of the flight control piece, one person in charge of the fuselage piece, they have to make a contract that says, okay, I need the flight controls as the fuselage. I need the flight controls to be able to do this, 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 and this. 4 things, whatever they are. As long as the flight control piece says, okay, here they are. Here's how you do it. I don't care in the fuselage how anything else happens. That's coding to an interface. And when we talked about interfaces a little bit earlier, I did mention that they're the idea of a behavior, right? So what you're really doing is you're modeling to a behavior. You're saying, my fuselage doesn't care how a flight control does what it does. It only cares that it has this behavior. And that's the idea of coding to an interface. That's why we call it coding to an interface. I'm going to check to see if we have any questions, because that's the conclusion of this first part of the series today, talking about designing software, how to decompose software into multiple pieces. Let me just find the responses. I have no questions yet. I'm sure that that does not mean that there aren't any questions out there, and that's totally fine. But for now, I'm going to go ahead and move on. All right, so let's pop back over to part 2. We're going to talk about, oh, you know what? There's one more piece into there, but I'm going to just throw this in there at the very end. So the next piece we're going to talk about is design patterns, right? This is another piece, sort of another related theme to designing software, is the concept of design patterns, right? And we haven't done much coding today, so I think what I'm going to do is, let's go ahead and try kind of messing around with some code. I'm actually going to, I showed you some interfaces, some abstract classes and stuff. Let's do a little coding thing. We're going to do a segue in here. So I had a great question earlier this week, and it was, somebody was working on some code, and I'm going to go ahead and stop that so you guys can, yeah, one of my students was working on some code, and he said, what I'd like to do is I'd like to be able to, I have this class here that I have created, and let me just pull it up and I'll show you. We'll just do this one right here. Yep, let me share that with you. Bam. So what he had was we'll go back with dog, right? We'll say it's a dog class. And his dog class had a name, it had a integer age, we'll say, it had a weight, it had a height in inches. And then his class also had what we call some getters and setters. So he had a method here called public void set name, string p name. And you'll see me do this occasionally where I'll name my variables like this, mname, mage. This is a kind of an older convention. You'll see it actually in Android all the time, where the name of a member variable, the member of this dog class, gets an m in front of it, whereas the parameter to a method gets a p in front of it. And so I can do stuff like this, mname equals p name. If I just give them both of these the word name, then it would be a little more confusing, right? I wouldn't know which one. I'd have name equals name. This doesn't make a whole lot of sense, right? That's kind of a confusing piece of code to see. There's a way around it. You can just say this dot name, which refers to the instance's member variable name. But I like to just do it this way because it's clearer. Everybody knows this means here, this means there. So I like to keep it that way. That's just my own personal thing. If you guys would like to, that's a fine way to do it as well. We're going to set age, int age. Every once in a while I forget to put it in there too. We're going to set weight. And I'll show you the problem in just a second. I just want to make sure you see this guy right here, height. And I did these two wrong, I know. I'll fix that right now. This is supposed to be a P. This is supposed to be a P. What he wanted to do is he wanted to say, well, here's my dog. In another class, he said, okay, I have this dog. I want to create a new dog. Dog d equals new dog. Then he said, and what I want to do is I want to say dog dot set name Fido dot set height 10 dot set weight 100 dot set age 20. 20 is old for a dog. Let's say 14. Still old for a dog, but not dead. He said, I want to do this. I want to chain these together. And some of you may have seen some method chaining. This is called method chaining, by the way. You may have seen this method chaining concept before. In fact, it's used a lot of times in JavaScript. You'll see it there all the time. He said, he tried to do this and it didn't work. He said, well, why can't I do it? And I said, well, the problem here is that when you call set name, it's returning a void. You see that? And a void in JavaScript means nothing. It means that there's no return. So when you call dot set name, it gives you back nothing. If you try to call dot set height on nothingness, it's going to fail. And it actually gave him an error. It said, you can't do that. There's no dot set height on the void object. There's nothing there to return back. But he really liked this. He thought it was clean. It was a clean syntax. So his question was, how do I do this in my own code? How do I make my code do chaining like this? So I'm going to show you guys a technique to do that. It's kind of simple, but once you see it, it's pretty useful to have. And this is a really valuable thing to be able to do if you're designing code that other developers can use. A lot of them are going to expect this kind of behavior. So I'm going to show you how to do that in your own code. And it's as simple as returning the instance that you're currently in. So now instead of set name and set age, all of these returning void, they're going to return this main class, this dog class. Right? And then instead of returning nothingness, they're going to return this. Now this means the current object, right? The one that you're in. So if you created a new dog, In this case, right here, this D, this dog is now a new dog. I'll rename him Fido. How about that? Right? That refers to, or that's what this refers to. This refers to Fido if you're talking about Fido.setName. And the reason that it does that is because you can have multiple dogs, right? You can have dog Sparky, new dog, right? And now when you call Sparky.setName, this refers to Sparky instead of referring to Fido. So you're just returning itself, basically. That's all you're doing is returning itself. But by doing that, you're now, when you call setName, you can now chain these methods together because setName, this here returns Fido with the new setName. So now Fido has a setHeight method. So you can set the height on Fido. This returns another instance of Fido, now with a new height. And you can set the weight right after that. So this technique allows you to chain methods together. And you can do this in any language. You can do it in JavaScript, Java, C++, you name it. And it gives you this really nice, clean API that you can use. You can chain the methods together. So that's kind of a cool little technique. It's my pro tip of the day. So that's how you design chained APIs. Alrighty, now I'm going to go ahead. That was kind of a little segue into the next section of code, or the next section of this, which is going to be design patterns, right? And this is kind of a complicated subject, but it's one that every developer should know about because it's something that, one, isn't taught in school, and two, I think should be. So what is, I guess the first question is, what is a design pattern really, right? Most people, you know, as a developer, when do you encounter design patterns? And it goes right back to the concept of engineering, right? In the 70s, we had the software engineering crisis. We said, how do we make software better? How do we make it have less bugs? Let's take a page out of the handbook of other engineering disciplines. And that's what they did. So if you think about any kind of physical engineering, a bridge, a building, that kind of stuff, you have these patterns that keep emerging in well-designed buildings. A good example is a triangle. As a shape is a very strong pattern. So you'll see a lot of buildings that are designed with triangles. You'll see triangle trusses on a house, for example. You'll see, triangle cable suspension on a bridge. That concept of having these pieces that have already been tested that we know work well, designed, those are architectural patterns. Those are engineering patterns. In software, we have them as well. And there was a book published. I'll find the name of it. It's called the Gang of Four. We call it informally the Gang of Four Design Pattern book. It was released in 1995, and that one laid out. It was a team of 4 engineers: Eric Gamma, Ralph Johnson, Richard Helm, and John Bliss Sades. They published a book in 94 actually, called Design Patterns: Elements of Reusable Object-Oriented Software. And the idea was, they said, we found these patterns that are consistent throughout our entire discipline. So they created they actually extracted the ideas out, codified them, and put them in this book. And the book that I'm going to recommend to you guys is Head First Design Patterns. Now, the design patterns, the original Gang of Four book, it's a little bit difficult for beginners to absorb. It's it was written for professional engineers who already knew the problems that were trying to be solved. But Head First Design Patterns, it'll actually walk you through all the problems and then how you use design patterns to solve them. So design patterns are essentially, some people even call it cheating, where you're saying, well, I already know how to solve this type of problem, so I'm just going to use this solution that I had from this other project. I'm going to use it in here. I'm going to use it in this idea here. And there are 24 of those design patterns in the original Gang of Four book. They're important as engineers because into design patterns. So Java engineers use them all the time. They're everywhere. In the Android system, you use all kinds of design patterns everywhere. So, and you may not even know, if you're in an Android program, if you're becoming an Android developer and you're newish to it, you may not even know that you're using these design patterns. And you might be wondering, why in the heck does an adapter do this? Or why does a recycler view use an adapter, as some kind of IAM adapter? And if this is over your head, don't worry about it. I'm not going to go any further. But you may be wondering that if you're an Android student. Why does it do these things? Or why does Android do this? And the reason is that it's a design pattern, right? They've stolen that idea, they've used that idea, and they've used it in the Android project. So why are patterns used? It's because you can now design interactions between your pieces of code. It goes right back to the idea of composition, where you're designing interactions between your pieces of code. And design patterns are basically just pre-canned interactions, right? How do these things work? So let's do this. I'm going to go over a couple of design patterns that you might see in Android, or actually in anything really. And the big one that you'll notice if you're doing any kind of programming in JavaScript, Java, one of the most common ones is the listener pattern, which would actually be called the idea of a listener. So a listener is a it's a function that gets executed, or it's rather a pattern where, for example, a button, right, gets clicked on, and a piece of code runs as soon as the button's clicked on. So the system doesn't want to sit there and wait. And this problem came from the UI world, right? This is a design pattern that came from UI, essentially, where a user would be using an application, they would click a button, and let's say the button was going out to the internet, downloading a huge file. If you weren't using the right kind of pattern, then when you click on that button, it's going to stay down until the download is finished. And that's not a very good user experience, right? So the idea came about, how do we fix this? What do we do with this? Well, what we can do is we can say, let's attach this method to the button so that when it gets clicked, and a method fires, right? This method gets called as soon as the button's clicked, rather than us sitting there and waiting for the button to finish whatever it was supposed to do. We can just say, well, go ahead and do what you're going to do, but let me move on, and then fire off something later as soon as the button's clicked, or as soon as this click method actually gets through, as soon as the button really is clicked. And so we'll go ahead and walk through a little bit of that. That's the listener pattern. That's just one example, or I should say the observer pattern, but you'll see them used as listeners all the time. Let me go ahead and show you exactly how that works. So we're going to create just a simple, this would be something you might see in an Android application. So I'm just going to use some of the Android terminology here. So let's say we have a class main activity extends base activity, right? And inside of this, we're going to say we have some buttons, right? This is a button on your Android screen. This will be the start button. We'll just leave it here for now, actually. Start. We'll have a checkbox, and we'll have, that's probably good for now. Don't worry about too much of this stuff right now. This is just kind of boilerplate Android. I'm doing it more because I know there are some Android developers out here going to be watching this. So I want you to have a full experience here. In Android, you call super.onCreate, and you would call set content view to some layout. Contains the button. And finally, you would say, get my button from that layout. By the way, don't be too worried about this yet. This is just for my Android students, so you guys have something to see here that you can actually try out on your machines when you get a chance. The idea here is that by the time you get to here, right, mStart contains a real button on the screen, and mCheck contains a real button on the screen as well. It contains a real checkbox, right? So that's the idea here, is by the time we get to this part of the code, mStart is a real button, mCheck is a real checkbox. So now we want to say, okay, Android's going to run my app, but I need it to be able to respond if somebody clicks on the button, right? And in Android, to do that with a view of any kind with a button, you attach what's called a listener using the start and the listener method. So every button in Android has this set on click listener, and we'll create a new click listener. This is just a click listener. This is just a class. This is all it is a class, and that class has a method in it. OnClicked. or on click rather. And inside of this on click method, do something once the button's clicked. This right here, this is the listener pattern. We created a new view, a new on-click listener that's going to fire off as soon as this button is actually clicked, right? So this function, this on-click listener is going to fire as soon as the button's clicked. And that means now my code, Android, can move on. It can do something else. It doesn't have to sit there and wait for the button to get clicked. Instead, it's just going to get called back. It's going to get this, this listener fired off as soon as the button's actually clicked. And you can do something with the button then, right? Otherwise, you don't have to sit there and worry about it. This observer pattern, this is the observer pattern, is a design pattern. It's something that some Android developers may not have even realized is there, but this is a design pattern. There are 24 of them. There's actually a lot of really interesting stuff that Android does that uses these design patterns. Another good example would be, let me see, pull up my notes here. What's called the strategy pattern. Now this was a good question. So this whole entire section came up because I had a student this week that was asking me what callbacks were. What's a callback? Some of you may not have heard the term. If you haven't, the idea is that a callback is a function that executes when you do something, which sounds kind of familiar, right? The difference between a strategy pattern and an observer pattern is that with a listener, for example, with our click listener here, that click listener is going to wait. It's the start button here is actually what says once I get clicked, search through my listeners right here, search through all the listeners that I might have on me and fire the on click method of that listener. So if I had a button class, I might have a, I'll have a piece of code that says for listener in my listeners, fire their on click method, right? And pass me into it. This would be code that you would actually see inside of a button class. And your set on click listener might look something like this. It might say void set on click listener. You might see something like this. This dot my listeners equals L, something like that. So this is the base of that pattern. It's really not anything too complicated. The observer pattern says that I'm going to have all these listeners, and me as the start button, I'm going to actually go into the listeners and call them when this click event happens, right? And I can have multiples of them. There's actually in Android, you'll see this convention where if you can only have one of them, they'll call it set, right? They'll say set on click listener. That says take something, if I had a click listener in there before, get rid of them and overwrite them with this one. They also oftentimes have an add method as well. There's an add on click listener. That will not overwrite the previous click listeners. That will instead just add one more method to the mix. So that'll allow it to have multiple things that can happen when a click is called or click is fired. That's the observer pattern. It says that I can have multiples of these listeners, and they're going to fire off when a button gets clicked here. The callback, the difference is that a callback, you're passing in an actual executable function that's going to fire as soon as this method is clicked or whatever, and it's not going to be called by the start method as a listener. It's not set ahead of time. It's passed in as soon as the click method happens. So if I were to do the strategy pattern, a callback in here, I would say mstart.onClick. And as soon as the click method happens, then I'm going to have this function that executes inside of here. This executes automatically as soon as the button is clicked. And rather than adding this to the mstart button class, I'm just firing it directly. This gets called one time as soon as it gets clicked, and then it disappears. There's no listeners that it has to cycle through. And inside of the button class, you'll see something like this. You'll have this method, void on click, and it's going to take a callback. And inside the onClick method, it's just going to call the callback. So in JavaScript, if this were JavaScript, it would look something like that, where you're passing in a function and then you're just firing that function as soon as this method's called. Now this passing in of a function, that's the callback. That's the strategy pattern. We're taking this function and you're actually passing it in as a parameter to something else, to another method. This is kind of a confusing one for a lot of people. The idea that you can take this function and actually pass it in, right? In Java, you can't use this exact syntax. You're going to have to create something called a callback, and it's a new type of class. But same idea it applies here, right? It's the same exact idea. This is just an executable piece of code that's passed in directly and called when the click happens. And the question might be, why would this be interesting or important? And what will happen in Java and in JavaScript as well, but Java often, is you'll have a task that you want to run separately from your main task. The good example is the UI. When you click the button, you want it to go out and download stuff and then come back, but you don't want the button to stay clicked down. You want it to be popped back out. You want to be able to interact with the screen still, right? You don't want it to just hang, because that's a bad user experience. So you can use these callbacks to say, for example, network.getWebsite, and you'll say google.com. And then you'll pass in a callback. It's going to fire as soon as the website is retrieved with the website text. Now this call right here, this is not a real call, but it's a general idea. This is pseudocode. But let's say you have a class network that lets you get a website. You pass in the URL and you pass in this callback that gets fired as soon as it's done. As soon as the URL has been retrieved and there's website text, then you're going to call, actually, you know what, I did this wrong here. I'm going to pass in this callback right here, right? And inside of my get website, it's actually going to fire this off. I did it right. I'm using this class. The website text exists here after the network returns the website. So this website text will exist, and it'll execute this function after the website text already exists. So if you're working with asynchronous programming, if you have a bunch of stuff going on at the same time, you can use a callback to guarantee that this website text will have been already retrieved, right? This right here will guarantee when you call this code inside of here, right? Display on the screen, we'll just make up a method that does that. That will guarantee that this method will work all the time, because this method right here, this function, this callback, will not get triggered or fired until this get website method has returned, until it's already retrieved the website. So you use callbacks when you have asynchronous code that's running in a different thread than another piece of code perhaps, or in a different set of execution. And this happens in JavaScript and Node.js in particular, very asynchronous. And you'll see this all the time. You'll see the callback pattern where they'll pass an error in a website text, and you'll say, if no error, then display the website text, right? And that pattern is used all the time. So that's the idea of a callback. It's used in asynchronous programming. Slightly different than a listener. How is it different again? A listener is attached to a button, and when you click on it, it cycles through every attached listener and calls each one. And a callback, the method you want to fire after an event occurs, is defined right in line in that function, and it's passed in. So this is passed into get website, whereas in the listeners, the click listener is attached to the button ahead of time. So it's not actually dropped in. It's not executed immediately after some kind of event or some kind of network return, for example. Instead, it's observing it. It's saying, okay, when a click listener when the click actually happens, fire off all my listeners attached to this start button. So that's the difference between those two. That's the async programming that's a callback, and that's the listener. Those are just two of many, 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 many design patterns that you're going to have the opportunity to work with. And the more coding you do and the more different languages that you learn, the more design patterns you're going to get good at. That's one thing that's been a common theme throughout my career is every time I've learned a new language or a new platform, I've learned a new set of skills. I've learned a new design pattern. I've learned a new way of doing things because each language was designed to overcome the downsides of another language, or they were designed to exploit a specific kind of pattern. And so when you learn that language, you learn the pattern as well. When I learned Perl, I learned how to use regular expressions really well. And if you want to see a good one on regexes, look at the previous lesson that I just did last week. When I learned Ruby, I learned about list comprehensions, which is something you can dig into later if you want, or I can do a show about it in the future if you'd like. When I learned Java, I learned a lot about design patterns in general. And every time I've learned a language, I've gotten to absorb a new idea, a new concept in programming. So it's a wonderful field in that you can never reach the end of the rabbit hole. You will always be able to dig deeper and further and find out more and learn more about it. And just when you think you're starting to get good, all of a sudden somebody's going to show you something that's just going to blow your mind. One of my favorite new concepts right now, something that I'm researching, is the concept of node-based programming, where you can write an entire application just using a visual editor and components. And I'll show you an example of something like that. There's a prototyping tool called Noodle, which you can use to, let me switch over to the Noodle program. You can actually use to prototype interactions between your code and other applications. And I did an entire interactive demo of a product that I'm working on entirely inside of this Noodle tool. And you can see here, this is a programming environment right here, but this is entirely node-based. So this code here, when you want to create a new visual element on the screen, all I do is right-click, and I'm going to create a new rectangle. For example, I create a new rectangle. Oops. And then I just attach it to wherever I want it to go. Right here underneath the footer, for example, I'm going to put it right here on the end of the transaction list. And you'll see in here, here's my rectangle that I just put in there. I'll stick it on top of my transactions here. And the possibilities are really endless. I'll make it a different color. And all the properties here pop up on the side when you're done. So you really have a lot of opportunity here. This is just one that I've been kind of prototyping and exploring lately. And I think it has a lot of potential. So here's my rectangle right here, just popped up. And I got the color here. I can change the blur radius, all that stuff. And I can attach all kinds of events to it as well. The other thing I really love about this is each one of these, you can create components here. So I can actually add this transaction list and this latest transactions. I can just double click this. And you can see that that latest transactions is actually a component, and it has multiple pieces inside of it. So this, by its nature, does composition exactly the way I've been talking about. This accounts page, right? It's over here. This is my accounts page. I'm going to double click it, and now it drills you down into the details. It has a body, it has a header, footer, add main account, which is this button right here. Let's go ahead and dig into the body. What's inside the body here? Well, it's got this scrolling list of transactions. So see, now I've got this component of body. And when you get to the top level, you don't really care. You've got this black box. I either have an accounts page, a latest transactions page, or a transactions list page. So for me, the concept up here, these main level components, they don't really matter as long as I know that this page is composed of these three components. And I can dig into each one of these as far as I want to go. The body, let's see what the body has. It's got a scrolling list of transactions with account items, right? So let's dig into an account item. Look at this account item. It's got all this complexity inside of it. It actually allows me to add different behavior outside of this component, right? And let me create a custom component, and I can do this stuff like dragging and adding new ones and stuff like that. All because I've got this app composed as a single high-level object, a single high-level system. And I just modeled the interaction between the system. So that's a good example, node-based programming, of new stuff that's coming out. And I love that this shows you really how engineering actually works. This is a black box, this is a black box, this is a black box, this is a black box. And you can see even this delete button, this is a black box as well. It's another component inside of this system. And that's how big software projects are built. That's a really great example of how big projects are done. Alrighty, and so I checked our questions. I didn't see anybody ask any questions or anything today, so I'm going to go ahead and let you guys go. Thank you for watching, and submit questions to me anytime you'd like. It's on the Code Your Face Off form. If you're just catching this on YouTube and you don't know where that is yet, you can go to cyfo.usefedora.com. I'm going to change the URL eventually, but for now it's cyfo.usefedora.com, and you can sign up for this live lecture. It's all free still. It's all free through Use Fedora as well. But if you go through Use Fedora, you're going to get some extra materials. I'm going to put notes. I'm going to put places to ask questions, and the link to ask questions to me is in there as well. So let me go ahead and pull that up. It's cyfo.usefedora.com, and yep, I'm going to stick a note. You know what I'll do is I'll put a note in the YouTube video. You can go to the link there and sign up for the course, and then you can see all the details and information about it. Alrighty, thank you very much for watching, everybody, and I'll catch you next time. Take care, and code your face off.